All right, so if the last video wasn't kind of clear enough, we can use what's known as the replacement test to determine how many peaks we're going to have in our proton NMR. And so we can have different types of protons. First off, there's heterotopic protons. And so this refers to the protons just being completely different from one another. So let's go ahead and take a look at an example of how we do this with the replacement test. And so here we have butane. We're going to take a look at this proton right here, and then its relationship to this proton right here. And so, I mean, I think you can kind of figure out that these two protons are different, right? One's on the end, one's in the middle. But you can use the replacement test to see this firsthand. And what we do is replace the H's with a D, with a deuterium. And so we'll replace this compound right here with a deuterium. Oops. Replace this hydrogen with a deuterium, and then replace this hydrogen with a deuterium. And then we take a look at the relationship between these two compounds. And so if you think about what's the relationship between these two compounds, is they're completely different or they're constitutional isomers. But either way, they're very different. And so their protons are different, and so you'll get two separate peaks from them, right? They'll show up as two separate peaks because they're different protons. Next up, let's take a look at homotopic protons. And so in this case, that means that they're the same. So let's take a look at ethane. And we can take a look at two different sets of protons. So let's take a look at these protons on the left and protons on the right, and we can try to replace them with a D, a deuterium. So if we replace this with a deuterium, and then replace this with a deuterium, and then we ask, what's the relationship between these? Well, if you just rotate the one molecule, it becomes the other molecule, and so they're the same. And so since these two molecules are the same, that means that these two protons are the same. And so you'll only get one peak from these two protons, right? They're going to appear as one peak. And same thing for the protons on one of these carbons of ethane, right? We can do the replacement test again. We'll get this one versus this one. And again, if you take a look at the relationship, these two are the same molecule. And so these two protons are homotopic, and so they appear as one peak. They appear the same. And so you can see if you take a look at the proton spectrum of ethane, you will only see one peak because all of the protons are homotopic with one another. Next up, we have enantiotopic protons. And the key thing to remember is these guys will still show up as the same peak. They're still chemically equivalent. Assuming you don't have a chiral solvent, which we won't encounter in this course. So let's go ahead and take a look at an example of this. So we'll have butane, and we'll take a look at this proton, and then this proton right here. And we'll do our replacement test. We'll replace each one of these with a deuterium, and then see what the relationship between these two are. So let me go ahead and make this a wedge and make this a dash. And so if you replace this one with a deuterium, you've got a D as a wedge here. And then if you replace this one with deuterium, you've got D as a wedge here. And so what you'll notice is that this is a chiral center now, right? By replacing that hydrogen with this deuterium, we've made it a chiral center. And so one's a wedge, one's a dash, they're in the same orientation. These two are enantiomers of one another. And so that makes these two protons enantiotopic protons. However, they still show up as one peak. Enantiotopic protons still show up as one peak, assuming we're not using a chiral solvent, which in this case, we will not. All right, and finally, this is probably the most tricky one, diastereotopic. Protons. And so if you haven't figured out the trend yet, when we do the replacement test, we're going to form diastereomers of one another. And so there's two main instances in which you'll see this. The first one being in alkenes. So for example, if we have propene, we can compare this hydrogen and this hydrogen. Are they same? Are they different? What are they? We can do the replacement test with one another. So replace this one with a D, and then replace this one with a D, and then let's see what the relationship between these two components are. And what you'll notice is that they're not the same. You cannot make these the same by rotating the molecule or anything like that. And so these are diastereomers, or two different compounds, right? One is E, one is Z. And so you'll see two distinct peaks, right? These two protons are not chemically equivalent. They are different. That's the first time you'll see diastereotopic protons. And then the other one is if you have a stereocenter elsewhere, right? So let's go ahead and draw this one right over here. And then we'll compare these two protons over here. Go like that. And so what we notice is that we have a stereocenter already here. And so we can label this stereocenter. This is an R stereocenter. And then we're going to do our replacement test. Again, we didn't mess with this alcohol, so this is both R in each situation. And then if you think about the stereochemistry of the other carbon, this one up here is R. Remember, D is above H but below everything else, while this one is S. So we have RR and SS. These two are diastereomers. And so what that means is that these two hydrogens are not chemically equivalent. They're different. And so we'll see two separate peaks here. So those are definitely the most tricky ones, right? So we have heterotopic protons, which are just almost completely different, right? It should be pretty easy to spot. Those will give you multiple peaks. We have homotopic protons, which means that they're the same. They're chemically equivalent. So you'll see one peak there. We have enantiotopic protons, which in our case are going to be the same as well. And so they'll just give you one peak as well. They're chemically equivalent. And then finally, we have diastereotopic and heterotopic protons, right? Those are not chemically equivalent. Those will give you two separate peaks for the two hydrogens you're comparing.